Hello, everybody. Welcome all of you to the first class of General Chemistry. My name is Henryk Witek. Henryk Witek. My specialty is quantum chemistry. And I have to tell you that it is bad luck for you. Because usually general chemistry is taught by experimentalists. I don't do any experiments. I do just computer simulation of chemical molecules and reactions. And in some sense, quantum chemistry may be considered as a part of physics rather than chemistry. So my point of view on chemistry is more physical than chemical. And that's what I will be trying to give to you. But the textbook you have is trying to emphasize the other way, the chemical way. And I think keeping the balance between the textbook and between the classes gives you a good image what chemistry really is, especially modern chemistry. Now I just wanted to hear a few words from you. So if I understand correctly, all of you are from the electric engineering department, right? So you are very intelligent and clever and you will understand everything at once. That's very good for me because I don't have to repeat anything twice. It's a very good feeling to teach good students. But I have to tell you, if you don't learn by yourself at home, you will not pass this class. You will fail. This is only your responsibility to pass this class. It's not business of mine if you pass or not. I don't get any extra money if you pass or opposite direction. So you have to learn. If you don't learn, you don't pass. I promise. Good? This is very important to make this part clear. Second point, this is university. This is not high school anymore. You don't have to come here. I never check any list. If there is 0 students, I go to my office and drink coffee. So if somebody thinks my class is not good, just don't come, learn from the book. If you can learn from the book perfectly well, it's fine with me. But if you find the class interesting or helpful, welcome, ask questions, discuss with me. I'm always open for discussions. Good. I see that everybody speaks English, more or less. I hope that during this class, your ability to speak and to listen to English will improve. The important part of this class, ask questions. Stop me any moment. If you don't understand something or you think that what I'm saying is wrong or I made a mistake, stop me immediately, okay? Any moment. Don't wait till the end of the class. Just stop now. Again, this is different than high school. In high school you have to be quiet. Here not. Here you are here to learn. I'm here to help you to learn. Okay? I'm here for you, not you are here for me. Okay. So ask me at any time any questions. Next important thing. Do not worry about English. Just speak slowly, slowly. We will understand each other. The point is that English is not my native language. Native language of mine is Polish. I'm from Poland in Europe. And the Polish language is very different than English. For example, chrząszcz brzmi w trzcinie, w Szczebrzeszynie. That was Polish, you see. Not very similar. So I make mistake when I speak in English. Probably I make a bit less mistakes than you make when you speak English. I don't know, maybe your English is very good. That would be nice. But anyway, all of us, we make mistakes when we talk. So don't worry. Don't worry, just try to talk, like me now. I try to talk without thinking if I make mistake or I don't make mistake. Doesn't matter. The understanding is important and the science is important. Language is on the side. Good. What are we going to study? We are going to start with the atom and with molecule. I guess you learn in high school many things about atoms and molecules, but I guess the point of view will be pretty different here. So we are going to learn something what is called electronic structure of atoms and molecules. And that's more or less how mathematics describes chemistry, how mathematics describes atoms, how mathematics describes molecules. What are the equations to solve? And what are the final solutions for these equations? Analyzing mathematical solutions, we are going to understand more chemistry. Later, when we understand how the single atom behaves and how a collection of few atoms connected together into a molecule behave, we are going to go to many atoms. So maybe 1 billion or maybe much larger number. And these atoms can have different types of concentrations. They can be gases, they can be liquids, or they can be solids, as you very well know. But we are going to treat, again, these three different states of matter from the point of view of physics, I would say, rather than chemistry. And at the end of this class, we are going to learn some chemical thermodynamics. Let us discuss now in more details each of these points. First, we start with atom structure. So we will learn that inside there is a nucleus, and this one you very well know. But outside there is no electron going around, nothing like that. There is one big cloud of electronic density, you may say. And inside this cloud, there is a nucleus. It will come later what it really means and how we really use it for anything, for predicting any properties or observables. These clouds are usually analyzed in terms of orbitals. Orbitals are purely mathematical objects. They don't exist in reality. Mathematical functions that are used for mathematical description of electrons. And these mathematical functions, they have some special properties. They have something what we call radial nodes and angular nodes. And according to the number of radial nodes and angular nodes, we classify the orbitals into different categories, as you see, 1, 2, 3, 4, or S, P, D, F. It will come later. We are going to discuss also Schrodinger equation. Since you are not ready for solution to Schrodinger equation, for solving Schrodinger equation by yourself, because it's quite complicated differential equation problem, and I guess you never studied differential equations before, then we are only going to discuss very shortly how to solve it and how the solutions look like. But we are not getting into the details. To be honest, if we want to solve Schrodinger equation for atoms, it would probably take us from 8 to 10 hours on the blackboard. And we don't have so much time. That's another point. Later, when we know everything about atoms, we are going to move to molecules. And we see that from the point of view of physics, atom and molecule is not so different. Instead of having one nucleus, you have many nuclei. And these nuclei are located in one big electronic cloud. The electronic cloud is not smooth. It looks more or less like that. And the maxima comes around each nuclei, but they are all connected. So we have one big cloud with some nuclei inside. You may say that it's a soup, boiling soup, when the water is the electronic cloud and inside the carrot, green pea are the nuclei. And we also have molecular orbitals. These are the functions, mathematical functions, again, not existing. Purely mathematical objects that describe us the electrons inside the molecule. And we are going to classify them as sigma orbitals, pi orbitals, delta orbitals. We are going also to say that they are bonding, on anti-bonding or no bonding. All of this will come soon. As you see some other strange words like delocalized orbitals, it will all follow. When we finish atoms and when we finish molecules, we will go to larger systems. So we are going to discuss the gas phase. And I'm sure that in high school you already learned something about gases and solids and liquids. So here there will be a repetition of this knowledge, plus some important extra information, like for example, kinetic theory of gases, or the concept maybe of ideal gas, plus the statistical description of the ideal gas. That's kind of interesting part and very nice mathematical. You can see everything and understand everything. A bit more difficult is in the liquid phase. Liquid, as a collection of molecules, they are all the time bumping into each other, is very difficult scientific object, and it's very difficult to describe it, and only really statistical description of liquids exist. And we are going to discuss some of the phenomena present for liquids like viscosity or surface tension, and we are going to understand the origin of them. Finally, we are going to move to solids, and to be honest with you, the solids will be dominated by crystals. There are also other solids that don't have internal structure, and we are not going to discuss them really. But for the crystal structure, we are going to discuss different types of Bravais lattices and close packing structures and also other structures. For this one, you have a lot of imagination. You have to have a lot of imagination to understand and see them. We'll be drawing a lot of models on the blackboard, and I hope that you will understand of this. After this part is finished, after we learn about solids, we move to thermodynamics. And what the word means. Thermo, it means temperature. So thermal, thermometer, connected to temperature, to heat. And dynamics means moving, science about moving. So totally thermodynamics is the science how the temperature makes particles move. And we are going to discuss two different thermodynamics here. One would be something called phenomenological. This is one of the most difficult English words I know. It takes some time before you learn how to pronounce it. So generally, phenomenon means something what you can see by your eyes or by your ears or by your tongue or by your hands, something what you can observe. So phenomenological thermodynamics is the thermodynamics of things that you can measure. Measure temperature, measure volume, measure pressure, things like that. These are exactly the temperature, volume, pressure. These are the words used for phenomenological thermodynamics. And the other one is a statistical thermodynamics. This is also interesting part, and maybe even more interesting to me than phenomenological, because here you look at the smallest possible members of the gas, liquid or solid, so usually at atoms or at molecules, and looking at these small objects, when they come together, go away, you try to understand how many of them will behave. So similarly, if you eat breakfast at 7 and you eat breakfast at 9 and everybody eats breakfast at some time, we can make average of your breakfast time and we finally find some plot. And we say that this class eats breakfast at this time. So this is similar thinking, statistical description of a large collection of objects. Phenomenological thermodynamics uses thermodynamic functions, and some of them, like internal energy, you already know. But the other one, I guess, like entropy, sorry, it should be enthalpy here, a mistake, I have to correct it. Enthalpy or Helmholtz free energy or Gibbs free energy, these things will be probably new for you. But you have to learn them, learn how to use them, and understand them. Then we are going to study the first and second law of thermodynamics that you probably already know from the high school. And we are going to use these two laws of thermodynamics to study chemistry. So, using these things, we are going to study chemical reactions. So we will say when the reaction happens, when it doesn't happen, when the temperature of the reactions go up, when it goes down. We are going to learn how to calculate the heat of the reaction, of this reaction, when we don't know this reaction, but we know this, and this. This is called Hess cycle. Then we define the equilibrium, so a state when the reaction doesn't go there or doesn't go there, when it stays at the same place forever. And finally, the most important maybe for chemists, we are going to learn when the reaction goes to substrates, products, and when it goes to the reactants. Good. That's maybe everything what we are going to study. Now, for me, it was always a very big problem to understand what is the difference between chemistry and physics. Very often the chemistry and physics come so close together that you don't know if you study chemistry or you study already physics. So there is no good definition of this. Many things are taught by physicists and chemists at the same time. Their viewpoint is a bit different. But today, we are trying to give roots to everything what we are going to study in this chemistry class from the basic physics. So we are going to study some particles, elementary particles, and elementary types of interactions to understand how important they are for our understanding of the world. So as you know, probably very well, there are four main forces in the universe. You know very well gravitational force, I guess. Electromagnetic force you know too, I guess, otherwise there would be no shadow here. But maybe the strong and weak forces may be something new for some of you. So, what I want really to say is that long time ago, there was no difference between these three forces. When the temperature is very high, there is hardly any difference between these forces. They are one and the same force, but when temperature of the universe is going down, these forces break symmetry and you can see them in a different ways. Now, gravitational force, you need mass that something can interact with gravitational force. So everything what has mass, and probably for you, everything what you know has mass, interacts with gravitational force. But the things that don't interact with gravitational force are neutrinos. They don't have any mass. For the electromagnetic charge, you need charge to interact. So everything what has charge interacts, but everything what doesn't have charge doesn't interact. For the strong forces, something needs to be colorful to interact. This sounds strange. How something can be colorful? What does it mean? Well, similarly like mass and charge is a word that you know very well. Because when you are a child and you grow, somebody says it's very heavy, it's very light. Or don't touch there is electricity there, it will spark you. But you can touch battery will not spark you. So you know these words because you grew up with these words. Nobody really knows. If I ask you, what does it mean, mass? It would be very difficult to explain. I don't know, to be honest, how to explain mass well. With the charge, if you come really basic level, I don't know how to explain it well either. I can try, but probably it wouldn't be good explanation. With the color, is similar thing. Color is the property of quarks. So every quark has a color. And if something has a color, then they interact with strong interaction. So generally, color is necessary for strong interactions, and the objects that can interact with strong interactions are quarks. How important are quarks for our chemistry class? We are going to discuss in a moment. Now, the other interaction called weak interaction, all particles interact. So this is important, but not for chemistry. It's important for physics. The reason is that this is the only interaction that neutrinos interact. Neutrinos have no charge, no mass, no color. They can interact only with the weak interactions. That's why it's so difficult to find neutrinos. Okay, so we know the basic 4 interactions. Now, we should also understand next important thing. My writing style is probably different than your writing style. So I want to tell you at the beginning that if I write this is A. If I'm going to write this, it can be R, or maybe sometimes it's V. Depends on my mood. So you have to just try to understand what I wanted to write. But V usually looks like that, or like that. Similar. What else? Next things. When I'm writing this, it can be 1. Usually you write like this. But sometimes when I'm in a hurry, I just write this. This is also 1. Okay? So you can ask me how I write 7. Usually you write 7 like this. But I very often write 7 like this. Okay? This is just to avoid problems in the future. I'm just telling you what can be on the blackboard and you don't know what it is. Here's the explanation. Okay, now we are going to discuss how strong are these interactions. Okay? So we are going to write relative strength. So the strong interactions are the strongest known interaction. Let's give them the strength 1. Then the electromagnetic are around 100 times smaller. So approximately 0.01. The weak interactions are much weaker, 10 to minus 13. And the gravitational interactions are the weakest possible. When I write 10 to minus 39s, it means 0, 39 zeros, and then 1. So looking at this picture, somebody may say, if I really want to calculate something or to understand something, I should include strong and electromagnetic interactions. These are not really important. And that's true. These two are really important. When you want to calculate something very accurately, you should introduce weak, but gravitational you can almost always forget. I never heard about anybody doing any corrections of gravitational force. Okay, so this is one important thing. Next important thing is distance. action. It means if I have one object and another object, how close they must be that they can interact with these forces. So it turns out that for strong ones, it's infinite. They always interact. For electromagnetic, it's infinite. For the weak interactions, this is really close. And for the gravitational one, it is again infinite. Now, very often here, the infinite is replaced by 10 to minus 15. I should put meter here. And to understand these two numbers, we should think like that. The strong interactions are an interaction between one quark and another quark. Now, the quarks never are separated unless the temperature is very high. So this is high temperature interaction range. But if you have low temperature, then the quarks are together as two quarks or sometimes as three quarks. And when these quarks are together, you have the cancellation of this infinite range and you have very short range like that. And next important thing, something is called asymptotics. Maybe I write it with, it's probably a new word for you. What does it mean, asymptotics? If I make a plot of the interaction, versus distance, the interaction is largest here and then goes to 0. Always, for any of them. Now the question is how it goes to 0. Now this one is 1 over r. This one would be 1 over r squared. This one would be 1 over r6. So you see that how fast they die is kind of important, because something may be very important only around here, like this one, but something may be important for a long, long distance. Sorry. Okay, and this power defines as the asymptotics of the interaction. So how fast something dies. So the asymptotics for all these interactions is as follows. For the strong one is 1 over r to the power 7. For the electromagnetic one, it's r to the power 2, and the same for the gravitational one. And for the weak one, it's not really well known. Maybe r to the 5, but maybe 1 over r to the 7. What is important here? The important part is that this one and this one, they die slowly. They go, are still non-zero, 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 non-zero. But these two, they die very fast. They go down, 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 and from here they are already 0. or very, very close to 0. So these are the important parts to know about the interactions. Okay, what is the structure of the book? We have to discuss it for a moment. So the first 90 pages or 100 pages, they are in green in the third edition and in blue in the new edition. This is the high school material. This one you should know by studying here. Then chapter 1 starts, says atoms, the quantum world. And then we are going to study up to chapter 7, including 7, which is 283 and starts at 1. So 300 pages, 280 pages. Now, out of these chapters, the last few pages are always questions, 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 exercises. And to be honest with you, the final exam and the midterm are very often just taken from here. You never know which one, but if you make all of them, then you are safe. Now, we already discussed what is inside the book, so if somebody wants to have a look later, can have. Okay, we know the book. Now we are going to study further the topic we started before the break. So we know the types of interactions. Now we are going to discuss what objects interact with each other. Now we know the forces. Now what objects interact with these forces. At the present level of knowledge, which may change in 20 years, particles are divided into two groups. One of them are called leptons. And other were called quarks. Okay. Now, what does it mean leptons? What does it mean quark? Lepton is coming from the old Greek word lepta, which means small, light. Turned out later that leptons not necessarily are so light and small, but when they made the name, they were small. Quarks is another name that's maybe 100 years old. It comes from a book by James Joyce. And means something strange, something odd, a particle that nobody wanted to believe at the beginning. Now, there are 6 leptons and there are 6 quarks. And this is all. There is nothing more. Everything what is more is made of leptons and quarks. And we are going to speak first what leptons and what quarks we have. We discussed this page already. Now we are going to leptons. We said there are 6 different leptons, and these are some of them that you know very well, like electron, and some of them you know very well, like neutrino. Turns out there are 3 different types of neutrinos. This makes sense because these 6 particles is divided into 3 families. Very light, heavy, very heavy. And electron has a heavy friend. The friend of electron is called muon. Muon and electron look very much the same, except that muon is around 2,000 times heavier. And they have very, very big friend called tau, or somebody say tau lepton or tau particle. And each of these three molecules, particles, electron, muon, and tau, have their own neutrinos. Now, neutrinos are completely non-interesting for us. The reason is they don't have mass, they don't interact gravitationally, they don't have charge, they don't interact with electrodynamic forces, they don't have color, no strong interaction. They only interact with weak interactions, and this interaction is so small that people are observing maybe 10 to 20 neutrinos per year in the laboratories in the Earth. So these are not important. They hardly interact with anything. Now, out of these three, this one is very, very heavy, less heavy, light. Now, when the temperature is very high, all three of them exist. When the temperature drops down, this one is decomposing into muon. When the temperature goes lower and lower, muon is decomposing into electrons. Now, around us in the cosmos, there are no tauns, no muons. All of them change into electrons in the light one. But if we hit the cosmos back, then we have all of them again. So out of these 6 leptons, only electron is the really important one. Neutrinos are everywhere. There are many neutrinos going through me now, all possible directions, but they don't interact. I don't feel them. So neutrinos are not important. They are like, I don't know what they are like, but not important. But muon and tau maybe are important, but in higher temperatures. Now, not. So the only important particle out of all leptons is electron. Let's go further to quarks. Again, we have 3 different families: light, heavy, very heavy. Now, the light quarks are called just simply and boringly up and down. A bit better names, strange and charm, are the next 2 quarks. And the last 2 were called bottom and top. Not many people is using the full name of quarks. Usually people are just use U, D, C, S, T, and B quarks. Now again, these quarks are very heavy. When the temperature is very high, all of them exist. When the temperature drops down, these 2 decompose into these 2. When the temperature drops down again, these 2 decompose into these 2. So virtually all the matter around us is made from up and down quarks only. This one, you cannot observe them in the real world, or that's not true. Sometimes you can observe them, but there is very small amount of them. But people make them artificially in accelerators. So we see that all the matter around us is really made by the up-down quarks and by electrons. Let us discuss how the mass looks like. So for the quarks, let's make a plot. Here would be charge. And here would be mass. So the lightest one, okay, first starts with charge. The charge of the quarks is minus 1/3 or 2/3. Sounds strange, 1/3 for charge. It sounds strange, 1/3 for a charge, but then why not? Electron has 1, why quark cannot have 1/3? I don't see a reason, to be honest. The only reason I see is that when I was a child, everybody told me that charge must be 1, 0, or -1. But 1/3 is fine too. So the quarks come as following. The lightest one is D. Next one is U. Then we have the S quark and the C quark. Then we have the B quark and we have the T quark somewhere here, but I just make the arrow T. What are the masses? Here is the mass. Here, people don't know. It's between 4 and 8. Here is between 15 and 40. You see, this is huge difference, but people never observe quarks separately. This one is between 80 and 130. This one is between 1050 This one is already becoming large, 4000. And this one is 171, 400, plus minus 2000. As you know from the Einstein relation, that energy equal mc square, so the relationship between the mass and the energy, something what has a mass like this can change into this mass and get larger speed or get a collision with another particle and give the energy to another particle. And that's exactly what is happening. This quark can go here. This one 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 can go here. Sometimes it happens that this one comes here. Sometimes happens that this one comes here. And that this one comes here. This is also possible. But the important point is that they can go down, they cannot go up. So if the down quark cannot become the up quark, but up quark can become down quark. This is important information to remember for now, because in a moment we are going to protons and neutrons and we are going to understand something important. Okay. So when the universe, when the cosmos was very hot, all of them existed. But later when the temperature started going down, all of them started going the processes down, and finally now we have only these two quarks left. A particle made out of 3 different quarks. 3 quarks together connected make a proton, and 3 quarks connected together makes a neutron. Now, UUD, UDD. When we look at this plot, we see that U is higher mass, higher energy than D. It means U can become D. It means that the proton can become neutron, but the neutron cannot become proton. So, this is the important information, because finally, at the end of the universe, at the end of the cosmos, everything will be filled with neutrons. There will be no protons left, because all of the protons go down to neutrons. So there will be no atoms, nothing left. And since electrons is the lightest of possible leptons, there will be neutrons and electrons only left. And photons, I would say, because this process is producing positrons, and the positrons will annihilate with electrons, giving photons. It's a bit more complicated, not important. But why neutron is heavier than the proton? I said that neutron is heavier than proton? Oh, then I made a mistake. Proton is heavier than neutron. Yeah. It's similarly like you look here. You have UUD and UDD. So the neutron is lighter, proton is heavier. That's why it can go there. Thank you for question. Good. And now, out of all possible particles, only these three compositions are important for making chemistry. Now, the science that is studying composition of quarks together is called quantum chromodynamics. I maybe write it down. So quantum chromodynamics is a science about quarks and the interactions between quarks. And this is part of theoretical physics, and we are not going to touch it here. Now, important thing is that at high temperatures, very high temperatures, quarks, UD, can exist separately. But at low temperatures, they can only exist in the groups of 3 or in the groups of 2. So we have the 6 quarks, and we have 3 quarks group. Quark group. Are called baryons. Hadrons. And hadrons comes from the Greek word for heavy. And you can make 2 quark groups. And this is called mesons. Now, how many different hadrons, how many different mesons exist? Well, you can see all the possible combinations and you can count as how many of them exist. But turns out that the quarks can have different colors. Usually they say about green, red, and I don't remember the third color, but there is a third color for quarks. So there are quite many combinations. I think people observed more than 200 different hadrons as so far. But they are not important for chemistry. They are high energy physics. And this science that discusses these groups is called particle physics. Again, hadrons can get together, like proton and neutron make a nucleus of a helium atom. This nucleus is a collection of 4 hadrons, and a science that describes collection of hadrons or collections of mesons is called nuclear physics. Good. Now finally times for chemistry comes. Chemistry is the science electrons interacting with nuclei. Can you see? So when an electron interacts with the nuclei, so the collection of hadrons, we have atom or we have molecule. And that's the moment where the chemistry starts. So Paul Dirac once said that chemistry starts in the moment when electron attaches itself to the nucleus. Then you have atom and you can start talking about chemistry. Okay. But why I said all of this? I just wanted that we not start from somewhere, from the sky. We started from the basic level and we constructed all the possible particles that we are going to discuss here, and you know how complicated already atom is. In the old Greek times, people thought that atom is a ball and you cannot do anything with this. Today, we think that the smallest particles are leptons and quarks, and you cannot do anything with them anymore. But it may change. People are not sure anymore. But the important point is that even if you can separate one quark into something smaller or lepton into something smaller, which I don't think you really can, you need very high energies, extremely high energies. And we don't have these energies in the Earth for the next 100, 200 years. So I think we are completely safe to understand this division and to define chemistry as a science of electrons interacting with a collection of hadrons, so with the atomic nuclei. Maybe just the last touch of this story will be the history of the cosmos, short history of the cosmos, how this all was created and when it was created. We don't know how it looked like. Not much information. And we don't know what was before, -1 second. Maybe there was something, maybe not. Anyway, if there was something, all the information was destroyed in the Big Bang. Big Bang destroyed all the information. Maybe there is time, maybe there is no time. Who knows? We just don't have access to this information. So in this moment, everything exploded and started going away from each other. All the particles, everything what was created in this one moment. It was a huge explosion. And now, after the time of 10 to -11 seconds, so very short time, the temperature was 10 to 15 Kelvin. In this time, there was no difference between weak and strong interactions. So weak, strong interactions and electromagnetic interactions, it was all the same in these very high temperatures. A bit time later, 10 to -9 seconds, look that these times are extremely short. Very short times. The temperature was lower. It was already only 10 to 14 Kelvin. Another thing. If I write this is 4. If I write this is 4 too. Okay? In this time, the third generation of quarks, heavy quarks, died. So in this moment, you have all possible quarks, all possible leptons boiling together like one big soup, and only one interactions between them. A moment later, the heavy quarks die. There are no more heavy quarks. The temperature is too low for them. They change into the normal heavy quarks. The time goes faster and faster, 10 to -8 seconds. here I should say very heavy quarks die. Here just the heavy quarks die. And quarks connect. So quarks connect into hadrons, into mesons. There are no more quarks left in this moment. And the time goes, 10 to minus 7, strange quarks die, and the nuclei are created. Then 10 to minus 4, the muon die, only electron is left. And finally at the 1 second, the first photons are created. Photons created. We didn't define photon yet. We have to define photon in a moment. And finally, after 700,000 years, first atom is created. And now it's around 10 to the 10 years after the Big Bang. So we see that for very, very long time, 700,000 years, there was no chemistry. The temperature must go very low that the atoms could be created. Before, the physics was taking over everything, and then the first atoms were created very late. And up to now, in this break, the atoms connected together and makes a molecule, and like in the earth, they make a human life, the chemistry of life. So this is a very short history of the universe with the position of the first atom created, and after that, the first molecules created. How the first molecules look like? You may say we don't know, that was so many years ago, but in fact we know. If you observe the stars, some of them are very far, and you still see this first atom being created, or first molecule being created. And what happens is that the first molecule look very strange. The first molecule looked like that, CH. Nothing else. You may say it's not correct, there is no such molecule. If you want to write a molecule, it would be CH4. This is true if you find 4 hydrogens. But if you don't find 4 hydrogens, but you find only 2 atoms, then there is a molecule created of 2 atoms only. And this is correct. And this is the difference between the high school chemistry and the university chemistry. In high school chemistry, if I teach you that you take hydrogen plus oxygen, then of course you can make H2O. I put here the N, whatever they are. This one you know. Something else? What can you make out of these 2 atoms? There is also H2O2, right? This one looks normally. Oxygen, hydrogen, hydrogen. This one looks like hydrogen, oxygen, oxygen, and now out of this plane there is another hydrogen sticking like that. So, hydrogen. Something else? To be honest with you, the list is long, maybe 100 other things, 100 other things, maybe 200, I don't know, but the list is very long. Because generally any molecule can be created. The only question you have to ask is how long the molecule exists. So for example, this molecule exists for a very long time. This one, after some time, will decompose into water and oxygen. All the others exist for very short time. Maybe 10 to minus 2 seconds, or maybe 10 to minus 10 seconds. This is very short times. These are unstable molecules. But in the cosmos, in the universe, when you have vacuum and two atoms meet, they can exist for a very long time because there is no other particles entering them and breaking them. But if you have a liquid or gas at Earth, when you have some pressure and collisions all the time, these are the usual living times of these particles. Okay, so just maybe 2 years ago, I've seen a scientific paper on this molecule. Looks very strange. It's C5H. Everybody normal would say, no, this is not a molecule. Somebody who wrote this formula doesn't know chemistry. But the point is, the person knows chemistry, but on the next level, on the level, university level. This is fine. This is okay. This exists. You can find what is the structure of this molecule. You can find what is the spectrum of the molecule. You can find the properties. And in fact, this molecule was observed somewhere far in some star. And that's the end for today. You had the introduction to chemistry. From the next class, we are starting real learning from a real book, real material. Will be more boring, I promise, from the next class. And I've showed you only the beginning, but the chemistry is much, much, much wider. For today, we have the following branches of chemistry. Analytical. This is the chemistry that is trying to find what and how much of each element or each molecule is in different places. For example, I have here grape juice, which is sweet, which is sour. Analytical chemistry will tell me how much sugar and what sugar, because there are many different types of sugars, and what type of sour taste is there, and what is the concentration of the hydrogen cations. Then you have maybe the largest possible chemistry, which is called organic chemistry. How many different molecules organic chemistry knows? To be honest, I don't know. I very often ask you a question, I don't know the answer. But maybe you know. But really many. I think it would be something like 10 to the 10 molecules. Many different types of molecules, really, huge amounts. There is a book called Beilstein, and this Beilstein is the book telling which molecules been made. If you try to put this book here, probably this is not enough space on this wall to put all the volumes of this book inside this room. This is huge books on this. And every year, millions of new chemicals are made by organic chemists. Next part is inorganic chemists, inorganic chemistry. And organic deals with carbon. Inorganic deals with everything except carbon. But these days, this is not really clear. So that was the definition before. Now, it's more traditional definition. Later you have physical, and that's the favorite one of mine, where you try to use the rules from physics to describe everything happening in the world around us, in the chemical world. Then you have, of course, quantum, when you try to use mathematics to describe the same things. Sometimes people say not quantum but theoretical, so I put them together. Next thing, if I write such thing, this is T. Okay, so this would be T. And this list is very, very, very long. Very long. I'm not going to write it down because it doesn't really make sense. But you have such strange thing like radiochemistry. Radiochemistry is using the radio waves to observe chemical very far in the stars, for example. So there are many, many different branches. How big is it? In meters. This is 1 meter. How big is the nuclei? So we have around 7 answers, 10 to minus 15. We have around 2 answers times 10 to minus 12, and we have around 5 answers times 10 to minus 10 for the nuclei. I think there was something like 10 to minus 10, and there was 1, 1, 1, 1 for 10 to minus 6, 7, 8, and 9, more or less like that. Okay, so now, this one depends on the atom, of course. But usually the size for the pink one is 5 times 10 to minus 15. Maybe twice larger for the big atoms. So that's more or less the size. So I have to say that not bad, not bad. And for this one, again, depends on the atom. And there is also another difficult point. This is electron cloud. It means it never finishes. 0, 0, 0, very small, but never finishes. We have to say what is the density of the cloud. And the density here is a lot of electrons, small, small, very small, almost nothing, almost 0, 0, 0, 0. So the question is where to bring the border, right? But usually what people say, they say 99% of the electrons must be inside and 1% can be outside. So if you put this definition of 99% is inside, then probably this one would be, let me think now, 1 to 10 times 10 to minus 10. So these answers are correct. So not bad. I'm very proud of you. That was a good test. We are going to have more tests like that in the future. Okay, so now you know the size. Next time we are going to speak about the mathematics of this cloud, how to describe it. Thank you very much.